Hi, today we will be discussing about Viterbi algorithm. The Viterbi algorithm is a dynamic programming for obtaining the maximum a posteriori probability estimate of the most likely sequence of the hidden state. And the sequence of the hidden state are called as the Viterbi path. Now, this Viterbi algorithm uses the concept of dynamic programming. Before going deep into the Viterbi algorithm, let us recap what the hidden Markov model speaks about. The diagram that is represented over here has two blocks, contains hot and cold. This hot and cold are the two weather conditions. These two weather conditions has three different unit that is called emissions that is marked as 3, 2 and 1. These emissions are called the observable states and the weather is called the hidden states. Similarly, for the weather cold, its observable states are again marked as 3, 2 and 1. This problem is called the ice cream weather problem, and here we have to identify what is the weather condition based on how many ice cream has been eaten by an individual. So the weather conditions over here, whether it is hot or cold, is hidden for the particular problem statement. We need to identify this problem based on the states that are to be observed. That is the number of items or the ice cream that has been consumed by an individual. Now, for current day, the weather can be hot. Now, following today's weather is hot, the next day weather could be cold, has the probability of 0.3. The change of one state to another state is called the transition probability. This helps to identify that probability of changing the weather from hot to cold or cold to hot is 0.3 or 0.4 respectively. Or the weather being on hot has the chance of getting hot in the next day also is also transition probability, and the probability here shown as 0.7 in this example. Similarly, for the weather cold, it is shown as 0.6. Now, we need to create the transition matrix from this state transition diagram. This diagram is called as state transition diagram. And from the state transition diagram, we have created the transition matrix by H representing hot and C representing cold in the rows, and H representing hot and C representing cold in the columns. And thus, for weather from hot to hot is been represented by 0.7, weather from hot to cold is been represented by 0.3, weather from cold to hot represented as 0.4, and so on. Similarly, we also create the emission matrix based on the state transition diagram. In the emission matrix, whether hot and whether cold has been represented and written in the row side, and the number of ice cream that has been consumed has been written in the column side. And for whether being hot and one ice cream has been consumed, probability is 0.2. Whether being cold, ice cream eaten 3 has the probability 0.1, and likewise the following matrix has been filled up. And the last one, pi is equals to 0.8 and 0.2 represents the initial state. Here the initial state, let us say, starts from weather hot. That means we are starting to calculate from the hot weather. That means the current weather is hot or day 1 is hot. The probability of the initial weather condition being hot is represented as 0.8, and the weather condition of the current state or the day 1 state is cold has been given as 0.2. This probability will be used to estimate the states of different days based on the ice cream consumed. We will see this in more elaborate in a quick example. Now let us look into the small example. Here the first one is written as hidden because all these state marked as H, C and H are the hidden state. These are the state that we need to identify. And the second part is written as observable. This is called the observable state where it is marked as 3, 1 and 3. These are the states that we can directly see or the computer can be allowed to observe. That means let us take an example of the ice cream weather condition that suppose this is day 1 and at the day 1 an individual has consumed 3 ice creams. That means based on the consumption of the ice creams, the state can be imagined or intuit as the weather is hot. Now, following the day 1, if the day 2 weather condition need to be identified, then the current weather condition has two dependency. The first dependency is the observable quantity, that how many or what is the conditions of the recent observable state, and based on that we can identify or the system can identify the hidden state of this particular day or the previous weather condition or the previous state. Now these two factors influence the present hidden factor, and by observing these two situations we need to identify, we need to um, estimate the present hidden state. Likewise it follows to the day 3. And here we have three observations, three ice creams, one ice creams, two ice creams and three ice creams. Now since we have three observations, so we can write that t is equals to 3 and we have two states, so n is equals to 2. Now for each observations, for day 1, for each observations that could be hot, that could have been cold also. Now for day 2, we can also identify this could have been cold or this could have been hot. This could have been hot or this could have been cold. So there could be a various combinations of hot and cold for each observations. Thus, we can say that total number of combinations that could have been possible is 2 to the power 3 is equals to 8. Now, for hidden Markov model says that we need to identify the probability of the entire combinations of this mm, hot and cold hidden state with respect to the observable state, and from there we need to identify the combinations that gives the maximum probability. This means that the formula that arises is probability initial state to the final state suggests that argmax into probability of 0 of ith state with q of ith state into p of qi such that q of I minus 1. Now we will see an example to elaborate this structure and to see the efficiency of the Viterbi algorithm in a few seconds. Now here in this example we are given three observable quantities. In the day 1, the individual has consumed 3 ice cream. In day 2, the individual has consumed 1 ice cream, and in day 3, again the individual has consumed 3 ice cream. Now from these three observable situations, the Viterbi algorithm will try to identify what will be the most appropriate weather condition based on the probability given on the state transition diagram that I have just recently showed to you. And from there, we also calculated the emission probability and transition probability matrix. From there, we will take the help from the table so that we can calculate the entire concept very efficiently. Now here on the top, I have written as V1, V2 and V3. These are the three Vitervis which we need to identify. Now let us consider we are calculating for the whether hot, given that 3 ice cream has been consumed. That means we can write in this way that 3 comma c, sorry, h is equals to p of 3 given h into p of h. Why we are writing p of h? Because here p of h is the initial state. Now here this h or day 1 state has been starting with value h. So we are considering p of h. We cannot consider any previous state values. Now here from the above table we can see that weather is hot and the individual has consumed 3 ice cream. The value is 0.4 and the initial probability of being hot is 0.8. So we apply this value. Zero point 4 into 0.8, we get 0.32. So we write here 0.32. Similarly, we calculate probability of 3 comma c. That means p of 3 given c into probability of c. Now here from the transition matrix and from the emission matrix, we get the values as 0.1. Provided the weather being cold, the individual has eaten 3 ice creams and this emission probability is 0.1, and the initial probability of being cold, that the day 1 will start from cold, has been given as 0.2. So 0.1 into 0.2 is 0.02. So here we can write this as 0.02. Now V1 for H and V1 for C has been calculated as 0.32 and 0.02. Now we need to calculate the next state H, and the next state H is depend on the previous state of H that has been recently calculated. So this H also has the influence on the next day being hot. So we need to identify the probability of current weather or the weather of day 2 being hot and the individual has consumed 1 ice cream is equals to probability of 1 given h into probability of today is h given yesterday was also h. So this was the emission probability and this was the transition probability. Thus, we can calculate the values of these probabilities to get the transition values from H to H. So let us identify the value. So H to H is 0.7 and H to 1 is 0.2. Zero point 0.2 into 0.7 is equals to 0.14. Now, similarly, we also find the probability of the day 2 will become cold provided that the yesterday was hot. So we need to identify P of 1 comma C on the conditions that previous day was hot. So P of 1 given C into P of C given H. Now the value we can get from the emission matrix and the transition matrix is 0.5 into 0.3 is equals to 0.15, and we can write this as 0.15. Similarly, we also need to find this condition and this condition in the similar process and in similar calculations. I give this calculation to your side. I'm just writing the answer. Now we have just calculated the transitions of this hot to hot or hot to cold or cold to hot or cold to cold. Now we need to identify the probabilities of these Viterbi for day 1, the weather being hot, and for the Viterbi in day 2, the weather being cold. So here what we need to do, we need to do the calculation coming from the previous Viterbi. So here 0.32 into first transition 0.14 and 0.02 into 0.08. Now if we do the calculation, it will give you 0.0448 and it will give you 0.0016. Now out of these two, we getting the maximum value as this one. So we write the value for Viterbi2, the weather being hot, is 0.0448. That means the maximum value is given for this path. Now for similar case, we also need to identify the path for cold. Now here also we will calculate 0.32 into 0.15 and 0.02 into 0.3, and thus the values are calculated as 0.048 and here it is 0.006. Now from these two values we will take the maximum value, and here the maximum value is 0.048. So 0.048. Now again similarly we will calculate the next state from this to this. Let us do it again. Now let us calculate the hidden state for day 3. Now day 3 hidden state depends on the observable quantity, that is the ice cream consumed, that is 3, and also the weather from the previous day, that means the weather from the day 2. Now here the day 2 weather was hot and day 3 weather being cold, and the observable item is 3, gives the probability as P of 3H. P of 3H is equals to P of the ice cream 3 such that the weather is hot into probability of weather being hot given that yesterday the weather was also hot. These two probability, first one is the emission probability, second one is the observable transition probability. Now putting the values from the above matrix, we can write as 0.4 into 0.7, which gives 0.28. Similarly, we calculate, this is 0.28, and similarly we calculate the probability transitions from hot to cold. Now the ice cream has been consumed as 3 given the weather is cold, and the probability of weather being cold given the previous day was hot. Thus from the emission matrix and transition matrix, we are writing the values as 0.1 into 0.3, giving 0.03. So here we write it as 0.03. Now similarly, we calculate this transition and this transition, and we calculate from the given transition and emission matrix, and we write the values. You are required to calculate this and write the values. I am writing the values directly. Now it is, the value is 0.03 and 0.06. I request you to calculate these values and check whether you are right or I am right or wrong, and verify the result with my given video. Now again we will calculate the Viterbi third. Now to calculate the V3, we need to take the help of V2 also. Now V2, along with the transitions, we need to identify the maximum value. Now here the value of B2 is 0.0448 into H to H gives the value 0.28, and for V2 being cold is 0.048 into cold to hot gives the value 0.03, and this gives me the value 0.012544, and here it gives 0.00768. Now from these two values, the maximum value is 0.0125. So here we write 0.012544. And similarly, we calculate for the cold weather, and it gives me 0.03 into 0.0448, and again 0.06 into 0.048. Here the values are 0.001344, and here it is 0.00288. Now from these two values, we will be considering this one, and we will write on the Viterbi. Now we have calculated all the posterior probabilities of these Viterbis. Now here, from these given calculated probabilities, we need to identify the Viterbi path. Now for every day, we need to identify the maximum Viterbi values. Now here the maximum Viterbi values is this H. On the day 2, the maximum Viterbi values is this one, because it differs with very little, but still 0.048 is higher than 0.0448. So if I do round off, it will become 0.45, but in the cold it is getting 0.48. So cold is more with respect to hot. Thus we have considered this cold, and again this one is the highest. So the Viterbi path that follows is day 1 is hot, followed by day 2 is cold, again followed by day 2, day 3 is hot again. Thus we can say that the combinations from of the hidden states are hot, cold and hot, and these are being obtained from the observable states along with the previous state of their weather conditions. Now if we have applied the normal HMM, then we need to identify 8 different combinations of these weathers provided given from these given observable states. Now the Viterbi algorithm helps us to store these intermediate values and helps us to calculate the next state with the help of these intermediate values, and finally it gives the idea whichever is the maximum, follow that path, and the combinations from this example is given as H, C and H. Thus Viterbi algorithm utilizes the approach of dynamic programming that helps us to reduce the time complexity from n to the power t to n square t. Thus, Viterbi algorithm is more efficient in providing the solution for a larger number of hidden states and observable states combinations.